The stars could be our next-door neighbors. This is the radical promise of the Alcubierre drive, a theoretical engine that manipulates the fabric of reality to achieve warp speed. By the end of this exploration, you will understand not just the tantalizing mathematics behind this idea, but the universe-shattering consequences of turning it into reality. We will confront a propulsion system that requires a form of matter that might not exist, and uncover why some physicists fear it could be the ultimate doomsday weapon. What does our enduring dream of sailing to the stars reveal about our deepest ambitions as a species? For millennia, the night sky was not a map but a tapestry of stories. Our ancestors looked up and saw gods riding chariots of fire, heroes ascending on beams of light, and mythical ships sailing the dark ocean between stars. This was not science, but a profound expression of a longing so deep it predates history itself, the desire to go there. That dream found new voice in the Age of Reason, through visionaries like Jules Verne and H.G. Wells, who used the emerging language of technology to ask, what if we could? By the 20th century, the dream had crystallized into an icon, the definitive whoosh and stretch of stars seen from the bridge of the Starship Enterprise, a warp drive that made the galaxy feel like a neighborhood. Yet for all its cultural power, it remained firmly in the realm of fiction, a fantasy for Saturday morning television. Then came Albert Einstein, and with his theory of relativity, the dream slammed into a wall of unforgiving mathematics. He showed us that the speed of light is not just a limit, it is a fundamental pillar holding reality together. Nothing with mass can ever reach it, let alone exceed it. For a species that had just learned to fly between continents, this was a cosmic verdict of imprisonment. Our solar system became a beautifully furnished cage. This frustration, however, did not extinguish the dream. It simply changed the question. If we cannot break the law, can we bend it? Physicists, those most disciplined of thinkers, began to look for loopholes in the universe's own rulebook. They started asking if the problem was our approach. We had been trying to move through space, but what if we could move space itself? This shift in perspective, from passenger to pilot of the cosmos, set the stage for a quiet revolution. It was this centuries-long arc of yearning, from myth to science fiction to scientific dead end, that prepared the world for a mathematician named Miguel Alcubierre to pick up his pen and ask one of the most audacious what-ifs in the history of science. The dream needed a blueprint, and in 1994, a quiet architect stepped forward with one. His name was Miguel Alcubierre, a theoretical physicist who approached the stars not with wishful thinking, but with a mathematician's pen. His goal was not to break Einstein's rules, but to explore their full potential, to ask if the equations themselves contained a hidden path forward. He framed the problem with elegant precision. How could a spacecraft appear to move faster than light to someone watching from afar, while the people inside the ship felt absolutely nothing, no crushing acceleration, no strange time distortions? The solution, he realized, was not to push the ship, but to move the road. Alcubierre's brilliant insight was to treat spacetime not as a static stage, but as a dynamic fabric that could be deliberately shaped. Imagine a surfer riding a wave. The surfer themselves is not paddling furiously to match the wave's speed. They are carried by the water's motion. Alcubierre proposed constructing a similar wave, not in water, but in the fabric of reality itself. He envisioned a stable bubble of flat, normal spacetime containing the ship. Then he would contract the spacetime immediately in front of this bubble, pulling the destination closer, while simultaneously expanding the spacetime right behind it, pushing the starting point farther away. The bubble and the ship within it would then be swept along this moving hill of spacetime, riding the geometry itself. Locally, inside the bubble, the speed of light is never exceeded and everything is calm. But to an outside observer, the bubble's effective speed could be staggering, potentially many times the speed of light. With a single, dense paper, Alcubierre had done the extraordinary. He had translated a science fiction fantasy into a set of mathematical equations that did not violate relativity. He gave the dream a formula, and in doing so, he transformed warp drive from a trope into a tantalizing, if distant, theoretical possibility. The architect had drawn the plans. Now came the daunting task of figuring out how, or even if, we could possibly build it. Alcubierre's mathematics revealed a beautiful and strange truth. The heart of his warp drive is not found in roaring engines or flaming exhaust, but in silent geometry. To build it, you would not be an engineer welding metal, you would be a cosmic sculptor, molding the very shape of reality around your vessel. The design is deceptively simple in concept. First, you create a safe haven, a pocket of perfectly normal, flat spacetime. This is your passenger compartment, where the crew would live and work under familiar physical laws, feeling no acceleration at all. Then you wrap this pocket in a breathtaking distortion, a bubble of warped spacetime that does all the work. The magic happens at the walls of this bubble. Think of space as a stretchy rubber sheet. Directly behind your ship, you would forcefully stretch that sheet, making it expand. This expansion does not move the ship. It moves the point of origin farther away, like pushing the dock out to sea from a stationary boat. Simultaneously, directly in front of your ship, you would compress the rubber sheet, squeezing space together to pull your destination closer. Your bubble of flat space is now sitting on a moving hill, a wave in the fabric of the cosmos, and it simply surfs this geometry to its goal. This elegant trick solves one of relativity's biggest headaches for interstellar travel. Normally, as you approach light speed, time slows down dramatically for you relative to everyone else, the famous twin paradox where one sibling ages while the other does not. But inside the Alcubierre bubble, you are not moving through space at high speed. Space is moving around you. Since your local environment remains normal, time passes at the same rate for you as it does for someone on Earth. You could travel to a star 100 light-years away and return, and only a few years might have passed for you, matching almost exactly the time experienced by those you left behind. This is why the geometry is so tantalizing. It promises not just incredible speed, but a kind of cosmic harmony, allowing us to traverse the galaxy without paying the terrible price of time. Yet to sculpt this miraculous bubble, you need tools, and according to the equations, the primary tool required is a form of matter so bizarre, it might not be possible to create at all. This is where the beautiful mathematics of warp drive collides with the stubborn physics of our universe. To sculpt that perfect spacetime wave, you need a very strange kind of paint. The equations of general relativity are clear. To create the specific curvature of an Alcubierre bubble, you require a form of matter that possesses what physicists call negative energy density. You might hear it called exotic matter, but that term barely captures its strangeness. Think of it as the opposite of everything we know. Normal matter, the stuff that makes up you, me, planets and stars, has positive mass and positive energy. It warps spacetime in the way we experience as gravity, creating the attractive pull that holds galaxies together. Negative energy density matter would do the exact opposite. It would warp spacetime in reverse, creating a kind of anti-gravity, a repulsive effect that pushes space apart rather than pulling it together. This is the essential ingredient for our warp bubble, the exotic material needed to compress space in front and expand it behind. So does it exist? The answer is a fascinating and frustrating maybe, but at scales that are almost comically mismatched. Quantum mechanics, the rules governing the very small, suggests that empty space is not truly empty. It is a seething quantum foam where virtual particles flicker in and out of existence. In certain constrained setups, like the gap between two incredibly close metal plates in what is called the Casimir effect, this quantum activity can create a tiny, measurable region with less energy than the surrounding vacuum. Technically, this is a minute amount of negative energy density. It is a real, laboratory-observed quantum phenomenon. The problem is one of scale. The negative energy produced in these experiments is infinitesimal, barely enough to influence the tiniest of particles. To sustain a macroscopic warp bubble big enough for a spacecraft, you would need to concentrate a staggering amount of this exotic material. Some calculations suggest you would need a mass of exotic matter equivalent to a large planet, or even a significant fraction of the universe's entire mass energy, just to create a bubble a few meters across. This is the first great showstopper. We have a brilliant design for a starship, but the only fuel that can power its engine is a substance we have only seen in ghostly quantum whispers, and we would need a cosmic stockpile of it. It forces a profound question. Is the Alcubierre drive a blueprint for a future technology, or is it a mathematical mirage, a beautiful proof that the universe ultimately forbids such shortcuts? Yet, even if we could somehow solve this impossible energy problem, the challenges would only grow more severe. But the exotic matter problem is just the first layer of a much deeper mystery. To truly understand the stakes of building a warp drive, we must look at what happens not to the ship, but to the universe around it. According to the mathematics, activating an Alcubierre bubble could create a terrifying kind of isolation. As the bubble forms and begins to surf its wave of distorted spacetime, a boundary emerges around it, a wall separating the interior from the rest of reality. This is not a physical wall you can touch, but a causal horizon, a point of no return for information. Think of it like this: once you are inside a warp bubble traveling faster than light, any signal you try to send forward, even a beam of light itself, cannot catch up to the front of the bubble to influence it. The crew would be completely cut off from the very mechanism propelling them. They could not steer, they could not adjust the warp field, they could not stop the process from inside. The journey becomes a pre-programmed roller coaster ride on a track laid down at the moment of activation, with no brakes and no way to change direction. This is more than an engineering flaw. It is a profound violation of how we believe the universe manages cause and effect. It suggests that within the bubble, the crew loses causal connection to their destination, becoming prisoners inside a self-contained pocket of reality. This leads directly to the most mind-bending consequence of all, the potential to shatter causality itself. The principle of causality is the bedrock of physics and of human experience, the simple idea that causes happen before their effects. You throw a ball, then it breaks a window. The sequence is inviolable, but if you can travel from point A to point B faster than a beam of light from certain perspectives, your arrival could appear to happen before your departure. This opens the door to the famous grandfather paradox, the theoretical possibility of traveling back in time and creating a contradiction, like preventing your own birth. An Alcubierre drive, by permitting effective faster-than-light travel, does not just move a ship through space, it tangles the timeline. Some physicists argue this is the universe's ultimate veto, a sign that such a geometry cannot be stabilized or that unknown laws of quantum gravity would prevent it from forming, precisely to protect the sequence of cause and effect. These are not simple puzzles to solve with better technology. They are fundamental warnings written into the fabric of reality, suggesting that the cost of stitching the galaxy together might be the unraveling of time itself. And if that were not enough, later researchers examining the drive's mathematics stumbled upon something even more startling: a hidden side effect that transforms the drive from a vehicle of exploration into something far more ominous. The dream of a peaceful journey to the stars hides a terrifying secret. As physicists dug deeper into the mathematics of the Alcubierre drive, they uncovered a side effect so severe it redefines the entire concept. Researchers, including scientists like Stefano Finazzi and his colleagues, realized that the warp bubble's walls would not be quiet boundaries. They would be frontiers of violent quantum activity. The intense warping of spacetime at the bubble's edges, the sharp boundary between the compressed space in front and the expanded space behind, would act like a powerful particle accelerator. It would spontaneously generate a storm of high-energy quantum particles, trapping them in a swirling maelstrom just outside the ship. This is not a minor technical issue. It is a fundamental consequence of marrying quantum theory with the extreme geometry of warp travel. The bubble would essentially carry its own apocalyptic weather system, a cloak of seething radiation clinging to its skin. The true catastrophe, however, comes at the end of the journey. When the warp drive is disengaged and the bubble collapses, that entire accumulated storm of particles would be released in a single, concentrated burst. It would be a blast of Hawking-like radiation, akin to the final evaporation of a microscopic black hole, but directed forward like a cosmic shotgun blast. Anything waiting at the destination, a planet, a space station, or even a fleet of welcoming ships, would be utterly obliterated. The energy release would be so profound it could sterilize an entire planetary system, turning a moment of arrival into an event of unimaginable destruction. Even the ship itself might not survive the backscatter from this detonation. In a single calculation, the warp drive transforms from a vessel of exploration into the ultimate theoretical doomsday weapon. Its mere activation could make the destination a tomb, rendering the entire journey not just pointless but genocidal. This grim possibility forces a profound ethical reckoning. It asks whether a technology that inherently carries such apocalyptic potential should ever be pursued, even in theory. It layers the already immense practical challenges with a moral dimension, suggesting that the universe may not just make warp travel difficult, but may fundamentally forbid it in any useful form to prevent such catastrophic outcomes. Yet the human mind, once presented with a puzzle, is relentless. Faced with these seemingly insurmountable barriers, from exotic matter to causal paradoxes to this radiation catastrophe, a small group of researchers refused to simply close the book. Instead, they asked a quieter, more subtle question. What if we are thinking about the shape of the dream all wrong? The dream's most radical shift came not from a lone theorist, but from a government lab. When the staggering theoretical hurdles of the Alcubierre drive became clear, a small group of researchers at NASA's Advanced Propulsion Physics Laboratory, nicknamed EagleWorks, decided to ask a different kind of question. They were led by physicist Harold "Sonny" White, and their mission was audacious. If we cannot build a warp drive, can we at least try to detect its ghost, a whisper of its physics, in a controlled experiment? Their goal was to move the concept from the blackboard into the realm of measurable, if microscopic, phenomena. This was the birth of the White-Jude warp field interferometer. The idea was to use a device called an interferometer, which splits a laser beam and measures how the light waves recombine. Any tiny warping of the space through which one beam passes would change its path length, creating a detectable shift in the laser's interference pattern. The team would not be trying to move a ship, but to see if they could induce a nanoscale distortion in spacetime itself, using carefully designed electromagnetic fields. They were hunting for the faintest echo of the Alcubierre effect in a vacuum chamber on Earth. The results, as one might expect, were controversial and hotly debated. Initial reports suggested the team had observed anomalous signatures, shifts in the laser pattern that could not be easily explained by conventional physics. These findings were met with intense skepticism from the broader scientific community. Critics pointed to potential sources of experimental error, from seismic vibrations to thermal fluctuations, arguing that extraordinary claims require extraordinary evidence, and that the evidence was far from conclusive. The debate was not just about data, it was about philosophy. Was this a legitimate, if high-risk, attempt to explore the boundaries of known physics, or was it a premature pursuit of science fiction? Regardless of one's stance, the Eagleworks effort represented something profoundly important. It was a crucial bridge. For the first time, someone was trying to build an apparatus to test a warp field equation, no matter how modestly. It transformed the Alcubierre drive from a purely mathematical curiosity into a catalyst for experimental innovation, pushing the limits of how we measure reality itself. While the specific interferometer experiments remain inconclusive and the Eagleworks lab is no longer active, that spirit of empirical questioning did not fade. It simply evolved, leading theorists back to their equations with a new directive, to find a version of the dream that might not demand the impossible. The sheer scale of the energy problem once seemed to be the final word on the matter. Early calculations based on Miguel Alcubierre's original equations delivered a number so large it felt like a punchline. To create a modest warp bubble, you would need to convert an amount of mass into energy equivalent to the planet Jupiter. Not just the physical bulk of Jupiter, but its entire mass energy content, a figure that dwarfs all the energy our Sun will produce in its entire lifetime. This was not a hurdle, it was a verdict. It placed the warp drive firmly in the realm of pure mathematical fantasy, a curiosity with no conceivable connection to reality. But theoretical physics is a living conversation, not a set of stone tablets. A decade after Alcubierre's paper, researchers began to look more carefully at the assumptions baked into those first estimates. They asked if the shape of the bubble could be optimized, if the walls of the warp field needed to be perfectly rigid and abrupt, or if they could be softer, more dynamic. This is where the story takes its most fascinating turn, largely driven by the work of Harold White and his team at NASA. By reimagining the geometry of the bubble itself, from a static ring into a more dynamic, oscillating shape, White's calculations suggested a staggering reduction in the required energy. The numbers plummeted from a Jupiter-sized requirement down to something on the scale of a large asteroid, and then, in some of the most optimistic revisions, to a mass roughly equivalent to the Voyager 1 spacecraft. Think about that for a moment. Voyager 1 is a probe we built and launched in the 1970s. It weighs about 722 kilograms. To go from needing the equivalent of the largest planet in our solar system to needing the mass of a human-made object floating in the void is a reduction so profound it changes the entire conversation. It shifts the warp drive status from physically impossible to merely technologically inconceivable with our current understanding. This is the power of theoretical refinement. It does not build the engine, but it can redraw the blueprints to show a path that is not obviously forbidden by the laws of physics. Naturally, these revised calculations are met with intense scrutiny and healthy skepticism within the physics community. Critics point out that the new models rely on specific, untested assumptions about the behavior of exotic matter and the stability of these oscillating warp fields. The exotic matter problem, while reduced in scale, has not vanished. You would still need to manufacture and contain a mass of this bizarre negative energy material. Furthermore, the other profound issues like the causal horizon and the destructive radiation burst remain entirely unaddressed by these energy optimizations. So while the journey from Jupiter to Voyager is a compelling narrative of scientific progress, it is not a declaration of victory. It is instead a demonstration of how a seemingly closed door can be cracked open just enough to let a sliver of light through, encouraging a new generation to look harder at what might lie beyond. If we grant for a moment that these energy and material problems could one day be solved, a new and equally daunting challenge immediately presents itself. How do you steer a vessel that is, by its very nature, cut off from the universe it travels through? The moment you press the button to activate a warp drive, you surrender all control. This is the stark reality of navigation within an Alcubierre bubble. Inside that pocket of calm, flat spacetime, you are not a pilot. You are a passenger on a cosmic roller coaster whose track was laid down the instant the field engaged. The ship is not moving through space. Space is moving around the ship, and that creates a profound and unsettling disconnect. Any thruster fire, any turn of a reaction wheel inside the bubble is utterly meaningless to your trajectory. You could spin the entire ship in circles, and it would have no effect on the direction the bubble is surfing through the warped geometry of the cosmos. You are, in the most literal sense, causally disconnected from the path ahead. This means your journey must be plotted with God-like precision before you ever begin. You need to know the exact position and velocity of every star, every planet, every sizable piece of interstellar debris along your route, not just at the moment of departure, but where they will be when you arrive. A miscalculation by even a fraction of a degree over a journey of light years could mean you emerge from warp inside a star or on a collision course with a planet. But the danger is not just from large objects. Consider a diffuse cloud of interstellar dust, harmless to a conventional starship shielded by magnetic fields. For a warp bubble, it could be apocalyptic. As the bubble moves, those dust particles are not simply passing by, they are encountering the violently warped spacetime at the bubble's boundary. They would be accelerated to incredible energies, potentially bombarding the ship with lethal radiation or destabilizing the delicate warp field itself. The act of stopping is equally fraught. How do you decelerate? The elegant answer is you reverse the process. You must somehow transform the exotic matter compressing space in front of you into the kind that expands it, creating a braking effect. But to do that, you need to be able to send a command to the front of the bubble, a signal that, because you are moving faster than light, cannot possibly get there. This implies the entire flight profile, acceleration, cruise, and deceleration, must be pre-programmed into the warp field generator itself, a single, unchangeable script for your voyage. So what would it feel like to ride inside this perfect, preordained capsule? The experience would be one of profound and eerie stillness. Through a window, you would see no streaking stars, no sense of motion at all. The view ahead might be a distorted lens, a swirl of compressed light, while behind you, a tunnel of darkness where stars are stretched into faint lines. You would feel no acceleration, no vibration, no sound. It would be the most serene and simultaneously the most helpless way to travel the universe, a silent, motionless box hurtling through a folded reality you cannot see or influence, entirely trusting in the mathematics that plotted your course to a destination you cannot yet perceive. The journey inside an Alcubierre bubble would be an exercise in profound sensory contradiction. For the crew, the physical experience is one of perfect, unnerving calm. The spacecraft and everything within it exists in a state of free fall, a zero-gravity pocket of normal space. You would float weightlessly, feeling no acceleration, no vibration, no hum of engines, not even the subtle pull of a distant star. It is the smoothest ride imaginable, a silent, motionless room. Yet this serenity exists within a maelstrom. If there were windows, the view would not be a comforting tunnel of streaking stars. It would be a terrifying distortion of reality itself. The intense compression of spacetime directly ahead of the bubble would squeeze incoming starlight, blue-shifting it to incredibly high frequencies. The gentle light from a distant sun could be transformed into a barrage of lethal gamma radiation, bathing the front of the ship in an invisible, deadly glare. Conversely, the expanded spacetime behind the bubble would stretch the light from your point of origin, redshifting it down into undetectable, deep infrared darkness. You would look behind to see nothing, a void where stars used to be. There is no sensation of speed, no passing landmarks, only the silent, placid interior of your capsule, juxtaposed against the knowledge that you are surfing a shockwave in the fabric of the cosmos. This disconnect is the ultimate expression of the drive's magic and its horror. The crew experiences a peaceful voyage, while just beyond the thin, mathematical boundary of their bubble, the universe is being twisted into knots. They are travelers in a pocket universe, utterly isolated, riding a geometric wave they cannot see, hear, or feel, toward a destination that holds dangers far beyond mere navigational error. The final, silent moments of a warp journey may hold the greatest danger of all. We have focused on the start of the voyage, the impossible fuel and the radiation storm clinging to the bubble, but the act of stopping, of carefully unloading this cosmic payload at its destination, presents a suite of challenges just as daunting. Decelerating is not as simple as turning off an engine. It requires a precise, controlled reversal of the immense spacetime distortion you have been riding. You must smoothly transform the compressed space in front of you back to normal, while calming the expanded space behind, all without creating a destructive shockwave in the fabric of reality. Think of it like trying to bring a tsunami to a gentle stop at the shoreline. The energy contained in that moving wall of water does not simply vanish, it must go somewhere. In the case of the warp bubble, that somewhere could be the release of powerful gravitational waves, ripples in spacetime itself, or a sudden lashing out of all the quantum energy accumulated during the trip. Even a seemingly perfect stop could leave behind a scar, a lingering distortion in the local geometry of space that might subtly tug on nearby planets, perturbing orbits over centuries in ways we cannot fully predict. This introduces a staggering ethical dimension to the dream. A civilization that masters warp travel would not just be building ships, it would be wielding a technology of planetary, even stellar, consequence. Every arrival would be an event that must be managed with God-like care and foresight. You would need to calculate the gravitational impact on the destination star system, ensure your deceleration path does not send disruptive waves through a region of space that might harbor delicate, undiscovered life, and guarantee that your vessel's grand entrance does not become an act of unintentional cosmic vandalism. The responsibility is immense, moving far beyond navigation and into the realm of celestial stewardship. It forces a profound shift in perspective. Warp capability is not merely a faster engine. It is a fundamental transformation in a civilization's relationship with the universe, elevating it from an inhabitant of spacetime to an active and perilously powerful shaper of it. This sobering realization about the local effects of arrival inevitably pulls our gaze outward to the grandest scales imaginable. If such a technology could one day exist, what would its repeated use across millennia do to the cosmos itself? The profound silence of the cosmos may be the loudest answer to our dream. For decades, the Fermi paradox has haunted our imagination, asking a simple, devastating question. If the universe is so vast and ancient, and life is even remotely probable, then where is everybody? Where are the great empires, the bustling galactic trade routes, the unmistakable signs of intelligence? The Alcubierre drive theory offers a chilling new lens through which to view this cosmic quiet. Perhaps the silence is not a sign of our loneliness, but of a universal physics that ruthlessly enforces isolation. Each of the drive's daunting barriers, from the exotic matter requirement to the Hawking radiation catastrophe, could represent what scientists call a great filter. These are not just engineering puzzles for humanity. They could be insurmountable walls for every technological species that ever evolves. The need for negative energy density might be a fundamental veto written into the laws of quantum gravity, a sign that the universe simply does not permit the kind of spacetime manipulation required for a stable warp bubble. Or perhaps civilizations do discover the secret, only to find that every activation of a warp drive unleashes a sterilizing blast of radiation at the destination. In that terrible scenario, any species that develops this technology might inadvertently use it just once, turning a neighboring star system into a tomb and learning a lesson so final it ends their interstellar ambitions forever. The silence, then, could be the echo of that single, catastrophic mistake repeated across the galaxy. There is another, more subtle possibility. A truly advanced civilization might master warp physics, but use it in ways that are deliberately invisible or undetectable to a young species like us. Their bubbles might be perfectly contained, leaving no energetic wake. Their arrivals might be so carefully managed, with deceleration paths calculated over centuries, that they cause no gravitational ripples we can sense. Or, having fully understood the apocalyptic potential and the ethical burden, they might make a collective, conscious choice to never deploy it, confining themselves to their home system or traveling at slower, safer speeds. The theoretical existence of the Alcubierre drive reframes the Fermi paradox from a question of biology or sociology into one of fundamental physics and engineering. It suggests that the stars might be quiet not because life is rare, but because the universe itself has built a cage from which there is no elegant escape, a cage of energy, causality, and consequence. This philosophical connection ties our most ambitious theoretical blueprint directly to one of humanity's oldest and most profound wonders. Yet, it is not the only blueprint on the table. To truly appreciate the radical nature of the Alcubierre concept, we must see how it stands apart from other proposed methods for crossing the interstellar void. The Alcubierre drive is a breathtaking idea, but it is far from the only path sketched out by theoretical physics. To truly grasp its place in our cosmic ambitions, we must see it alongside its conceptual siblings, each offering a different answer to the same impossible question. One such sibling is the traversable wormhole, a shortcut stitched through the folded fabric of spacetime itself. Like the warp drive, wormholes emerge as valid, if exotic, solutions to Einstein's equations. Imagine the universe as the surface of an apple. A wormhole would be like a tunnel bored directly through the fruit's core, connecting two distant points on the skin in a single step. You would not travel the long way around the surface. You would take the interior passage, potentially crossing thousands of light years in an instant. The appeal is immediate and profound, but the familiar devil is in the details. Just like the Alcubierre bubble, a stable, human passable wormhole would require copious amounts of exotic matter with negative energy density to keep its throat propped open against the natural tendency of gravity to crush it shut. Furthermore, even if stabilized, stepping into a wormhole could be a one-way trip into the unknown. There is no guarantee the other end would be where or when you expect. The equations allow for the terrifying possibility that wormholes could also function as time machines, creating the same causal paradoxes that haunt faster than light travel. So while both concepts, warp drive and wormhole, are born from the same elegant mathematics, they present a stark choice in theoretical risk. The warp drive is a controlled, moving distortion you carry with you. A wormhole is a fixed but potentially unstable piece of cosmic infrastructure. One is a ship, the other is a bridge, and both demand building materials that may not exist. Then there is the option that requires no new physics at all, only immense patience and profound societal commitment, the generation ship. This is not a vessel of magic, but one of sheer endurance. A generation ship would be a colossal, self-sustaining ark, perhaps miles long, carrying a complete human civilization. It would embark on a voyage lasting centuries or even millennia, traveling at a significant fraction of light speed, but still bound by Einstein's ultimate speed limit. The crew that departs would not be the crew that arrives. Their children and their children's children would be born, live, and die within the metal walls of the ship, their entire universe a long corridor hurtling through the dark. The destination star is a distant point of light their ancestors pointed them toward, a promise they themselves will never see fulfilled. This concept trades the terrifying physics of warp drive for equally daunting challenges of biology, sociology, and engineering. Could a closed ecosystem remain stable for 10,000 years? Could a society maintain its purpose and sanity across hundreds of generations born into transit? The generation ship accepts the tyranny of distance on its own terms, using time itself as fuel. It is a sobering mirror to the warp drive's promise of quick, easy hops. One says the universe can be tricked, the other says we must simply outlast it. Placing the Alcubierre drive between these two extremes reveals its unique and peculiar character. It is more audacious than the generation ship, refusing to accept the slow march of time, yet it is arguably more controlled than the wormhole, a vehicle with a defined departure and arrival, rather than a plunge into a fixed cosmic tunnel. Its greatest allure is that it promises to preserve the human scale of the journey. You could, in theory, leave Earth, visit a star, and return within a single lifetime, greeting the same friends and family you left behind. It offers the dream of exploration as we have always known it, just on a grander canvas, but its demerits are equally unique. The generation ship, for all its hardship, leaves the universe untouched. The warp drive, with its radiation burst and spacetime scarring, arrives as a potentially destructive event. The wormhole, if it could be built, becomes permanent infrastructure. The warp drive is a transient weaponization of geometry. This comparison does not tell us which idea is right, but it clarifies the stakes. Each concept represents a different bargain with the cosmos, a different set of risks we would have to master, not just as engineers, but as a civilization. And these are not just abstract ideas confined to scientific papers. They have seeped into our stories, shaping how we envision our future, and in turn, inspiring new generations to look at the equations once more. That quiet mathematician's paper did more than reshape equations. It reshaped our collective imagination. The Alcubierre drive represents a rare and beautiful moment where science and science fiction entered into a direct conversation. For decades, fictional warp drives, most famously in Star Trek, inspired generations of scientists and engineers. Miguel Alcubierre then performed a kind of alchemy, taking that fictional trope and translating it into the formal language of general relativity. But the story did not end there. His work flowed right back into the realm of storytelling, arming a new wave of creators with something powerful, a veneer of real scientific plausibility. This is most evident in films like Interstellar, which, while using a wormhole as its central plot device, leaned heavily on the advice of physicist Kip Thorne to ensure its cosmic visuals were grounded in real equations. The swirling, lensed light of Gargantua was not just artists' fancy. It was a calculated depiction of a supermassive black hole's accretion disk, a direct gift from rigorous theory to blockbuster spectacle. This created a feedback loop of inspiration. The drive became a symbol that the most audacious ideas were not off-limits, that they could be held up to the light of mathematics and examined. It told the public that theoretical physics was not just about abstract particles, but about confronting the grandest what-ifs of our species. This cultural impact is profound. The Alcubierre drive, by existing in that liminal space between confirmed fact and tantalizing possibility, has fueled public interest in fundamental science in a way few other concepts have. It makes headlines not for a new discovery, but for a new calculation, a new tweak to the geometry that brings the dream a nanometer closer. It represents humanity's aspirational side in its purest form, the stubborn refusal to accept no for an answer, and the discipline to test that refusal against the unforgiving rules of the universe. This interplay between wild imagination and rigorous calculation is now a defining feature of how we explore the cosmos, both in fiction and in fact. It proves that dreaming is not the opposite of science, it is often its essential first step. and today that dreaming is focused with laser intensity on the drive's most infamous flaw, the demand for a substance that might be impossible to find. The equations on the page are not a final verdict, but an invitation to a deeper conversation. While the fundamental hurdles of the Alcubierre drive remain, theoretical physicists have not walked away from the puzzle. Instead, they have picked up more sophisticated tools, asking if the original blueprint can be redrawn using insights from our most advanced theories of reality. This is not about building a warp engine tomorrow, but about probing the absolute limits of what the laws of physics might permit. The quest has evolved into a vibrant, if highly specialized, field of academic study, where new papers are published every year exploring subtle modifications to Miguel Alcubierre's original metric. These researchers are not science fiction fans. They are mathematicians and theorists treating the warp drive as a fascinating stress test for our understanding of the cosmos. One promising avenue involves bringing quantum field theory into the mix. The original model treated spacetime as a classical, smooth fabric, but we know that at the very smallest scales, spacetime likely has a foamy, quantum nature. Some proposals suggest that by properly accounting for these quantum effects, the horrific negative energy requirements might be significantly reduced or perhaps even cancelled out by other quantum phenomena. It is a bit like discovering that a building material you thought was impossibly rare might be synthesized from common ingredients, if only you understand the chemistry at a deeper level. Another line of attack reconsiders the very shape of the warp bubble itself. Could a different geometry, one that doesn't create such sharp, pathological boundaries, avoid the deadly radiation problem? This has led to investigations into what are called subluminal warp bubbles. These are designs that explicitly forego faster than light travel, accepting Einstein's ultimate speed limit, but still use the same principle of moving spacetime to achieve a significant fraction of light speed incredibly efficiently. Imagine a vessel that can cruise at 99% of light speed without needing to carry mountains of conventional rocket fuel. While not as flashy as jumping to Alpha Centauri in a week, such a technology would still revolutionize our place in the galaxy, making interstellar journeys feasible within a human lifetime. Even more speculative are explorations that tie the concept to the frontiers of theoretical physics, like string theory or loop quantum gravity. These frameworks attempt to unify gravity with quantum mechanics, and they suggest that spacetime may be built from discrete pieces or vibrating strings. Could such a fundamental rewriting of reality's rules provide new mechanisms for warping it? The papers are dense, filled with tensors and complex derivations, and their conclusions are tentative. Yet their very existence is meaningful. They demonstrate that the core idea, manipulating spacetime for propulsion, is a legitimate and enduring topic of scientific inquiry. It is a long-term investment in curiosity, a way of mapping the outer boundaries of the possible. This sustained, rigorous investigation forces us to confront a critical question. Where does the Alcubierre drive truly stand in the landscape of modern physics? Is it a guiding star for future technology, or is it something else entirely? For every visionary blueprint, there are those who study the fine print and find it wanting. The most compelling critiques of the Alcubierre drive do not come from a place of closed-mindedness, but from a deep commitment to the established rules of the game. Mainstream theoretical physicists, while acknowledging the mathematical cleverness of the model, point to a foundational issue they believe renders the entire concept a mirage. Their central argument is this: the requirement for exotic matter with negative energy density is not a challenging engineering problem, it is a fundamental showstopper. It is what philosophers of science call assuming the conclusion, or in simpler terms, putting the answer into the question. You begin by stating you need a substance that warps spacetime in reverse to build your warp bubble. but such a substance, in the macroscopic, stable quantities required, has never been observed and is strongly argued by many to be impossible under known physics. The tiny quantum effects like the Casimir force are not a stockpile of this material. They are a fleeting, microscopic phenomenon in a highly constrained environment. To build a warp drive, you would need to scale this ghostly whisper into a deafening shout, and the laws of quantum field theory suggest that such a concentration would be violently unstable, collapsing instantly or violating fundamental energy conditions that prevent paradoxes. From this skeptical viewpoint, the Alcubierre drive is not a theory of propulsion. It is a mathematical curiosity. It is a solution to Einstein's equations in the same way that dividing by zero is a solution to an algebra problem. It is technically permitted by the symbols on the page, but it leads to a result that has no connection to physical reality. These critics warn of the opportunity cost of fascination. They argue that devoting significant intellectual and financial resources to what they see as a phantom chase distracts from more plausible, incremental research that could yield real benefits. This includes advanced plasma propulsion for efficient solar system travel, nuclear thermal rockets, or the monumental but physically grounded engineering of generation ships and orbital habitats. Their plea is for clear-eyed perspective. It is thrilling to speculate about bending space-time, but a responsible scientific and technological agenda must prioritize pathways that do not require rewriting the known laws of physics as their very first step. This critical counterpoint is essential, not to crush the dream, but to ground it. It reminds us that the most awe-inspiring journeys begin not with a leap into the unknown, but with an honest assessment of the ground beneath our feet. Yet, even with this sobering skepticism laid bare, the human impulse to look forward remains undimmed. If we allow our imagination to travel down the road not yet taken, what might a civilization that has truly mastered spacetime actually look like? The scale of the problem reveals the scale of the solution. Our current struggles with the Alcubierre drive's energy demands make sense when we remember we are a Type 0 civilization, still tethered to the energy of a single planet. But the universe operates on a different level of power altogether. To find a context where warp drive might be plausible, we must look not decades ahead but millennia, to a future humanity that has fundamentally transformed its relationship with energy and matter. This is the realm of the Kardashev scale, a way of classifying civilizations by their energy mastery. A Type 2 civilization does not mine planets or burn fossil fuels. It has encapsulated its entire star within a vast energy-harvesting structure, a Dyson sphere or swarm, capturing nearly all of its solar output. For such an entity, the energy equivalent of a planet like Jupiter is not an impossibility. It is a manageable line item in a stellar budget. The astronomical figures that stymie us become trivial engineering challenges. The exotic matter requirement, while still a profound physics puzzle, becomes a different kind of problem. With the energy of a sun at its fingertips, a Type 2 civilization could undertake construction projects on a scale we can barely conceive, perhaps manufacturing the necessary spacetime conditions in vast orbital foundries, or manipulating quantum fields across regions of space larger than our solar system. In this light, the Alcubierre drive undergoes a dramatic shift in identity. It is no longer a potential next step for our rockets. It becomes something else entirely, a post-scarcity technology. It is the kind of tool you only invent after you have solved everything else, after you have mastered your home system, achieved material abundance, and seek only to connect with other islands of light in the galactic ocean. The drive transitions from a propulsion system to an artifact of cosmic maturity. This long-view speculation is crucial because it reframes the entire conversation. We stop asking if humanity can build a warp drive in the next century, a question that likely has a disappointing answer. Instead, we ask what kind of civilization would be required to build one at all. The answer paints a portrait of a society so advanced, so secure in its energy and knowledge, that the very act of folding space is not an existential risk, but a deliberate choice of exploration. They would have the computational power to model the gravitational waves of their arrival across entire star systems, the engineering wisdom to contain the Hawking radiation burst, and the ethical framework to use such power without causing harm. For them, the drive is not a weapon, it is a passport. This perspective is simultaneously humbling and inspiring. It tells us that the stars may not be for the taking by a species like ours, still struggling with its own planet. They await the arrival of a wiser, more stable version of ourselves, one that has earned the right to surf the geometry of the cosmos. And if such civilizations do exist out there in the silence, their tools would be so far beyond our understanding that we might not even recognize the traces they leave behind. The drive does not just challenge our engineering, it challenges our philosophy. For centuries, we have thought of space as an empty container, a passive stage where matter performs. The Alcubierre concept shatters that intuition. If you can squeeze space in front of you and stretch it behind, then space is not just a backdrop. It is an active participant, a dynamic substance with properties that can be manipulated. This raises a profound question: is spacetime a real, physical thing, or is it just a useful mathematical diagram, a set of relationships between objects? The warp drive suggests the former. It treats spacetime as a kind of cosmic material, something that can have a shape, a tension, and perhaps even a texture. This shifts our entire perspective on travel. In a conventional rocket, you are an object moving along a path. In a warp bubble, you are not moving along the path, you are bringing the path with you. The vehicle and the roadway become one and the same. Your location is no longer a simple dot on a map. It is defined by the unique geometry of the bubble you carry. You are, in a very real sense, carrying a piece of folded universe. This blurs the lines in a way that feels almost magical, yet it emerges from cold, hard equations. It forces us to see the cosmos not as a fixed arena, but as a malleable landscape, and ourselves not just as wanderers, but as potential sculptors. These are not just abstract thoughts for philosophers. They strike at the heart of modern physics, where the nature of spacetime is the greatest unsolved mystery. By trying to build a warp drive, even on paper, we are conducting a radical thought experiment that probes the very fabric of reality. It asks what the universe is made of at its most fundamental level, and while we may never construct the engine, the questions it forces us to ask are yielding answers in unexpected places. This high-stakes philosophical inquiry, it turns out, is already paying practical dividends here on Earth. Sometimes the most valuable discoveries are not the ones we set out to find. The relentless pursuit of the warp drive, even as a theoretical exercise, has already begun to pay unexpected dividends across the scientific landscape. This is the powerful spin-off effect, where the quest for one impossible dream illuminates countless other paths forward. The intense mathematical work required to probe the Alcubierre metric is not a solitary endeavor. It is a rigorous stress test for our entire understanding of physics. To even ask if a warp bubble is possible, researchers must push the tools of general relativity and quantum field theory to their absolute limits. They develop new techniques for modeling exotic spacetimes, for calculating energy conditions, and for understanding how matter and geometry interact under extreme circumstances. These are not abstract skills. They are directly applicable to some of the biggest mysteries in the cosmos. The same mathematics used to analyze the stability of a warp bubble's wall can help cosmologists understand the inflationary expansion of the early universe, a period when spacetime itself expanded faster than light. The insights into negative energy and quantum fields refine our models of black hole evaporation and the strange physics of the event horizon. In essence, by trying to engineer a tiny piece of curved spacetime for a ship, we get better at reading the grand, natural curvatures written across the heavens. This intellectual cross-pollination is a hidden engine of progress. Furthermore, the sheer allure of the topic acts as a gravitational pull for public imagination and support. A complex paper on quantum field theory might gather dust but frame it within the context of a real-life Starship engine, and it captures headlines. This engagement is not trivial. It inspires students to pursue careers in physics and mathematics. It helps justify funding for advanced research in foundational science, the kind of research that may not have an immediate application, but which builds the bedrock for future technologies we cannot yet envision. The story of the warp drive teaches a profound lesson about how science often works. We aim for the stars, and along the way we invent the telescope. The true value of this decades-long thought experiment may never be a working engine. Instead, it is the deeper map of reality we are drawing with every calculation, and the renewed sense of wonder that fuels our entire journey of discovery. This positive outlook, however, must be tempered with a sobering responsibility. A starship is not just a vehicle, it is a declaration. To possess the power to fold space and cross light years in a heartbeat is to step onto a galactic stage with consequences we can barely fathom. This is not merely an engineering milestone, it is an ethical transformation of our entire species. The terrifying Hawking radiation burst we discussed is not a minor engineering flaw, it is the ultimate warning label. It means your engine is also a weapon of stellar annihilation, and the act of arriving at a new world could, with a single miscalculation, render that world a lifeless cinder. This power forces us to confront responsibilities on a scale humanity has never before considered. We would become interstellar actors, and every journey would carry the potential for accidental cosmic vandalism. But the ethical questions extend far beyond the physics of arrival. Consider the quieter, more insidious risks. A warp-capable civilization arriving at a planet with a nascent biosphere could unleash catastrophic contamination. Our microbes, harmless to us, might be an alien plague, wiping out entire ecosystems before we even step out of the ship. Conversely, an alien microbe could pose an existential threat to us. The prime directive from science fiction ceases to be a narrative device and becomes a necessary survival protocol, a first principle of interstellar ethics. Then there is the question of resources and contact. If we found a system rich in rare materials, would we mine it, potentially disrupting a delicate cosmic environment? And if we encountered another intelligence, how would we approach them? Our history on Earth is a chronicle of conflict born from fear of the different. Could we overcome that deeply ingrained instinct when meeting a consciousness that might be utterly alien in form and thought? These are not future political debates. They are foundational questions we must answer before we ever attempt to build such a machine. The development of warp capability cannot be a race won by physicists and engineers alone. It demands a parallel and equally rigorous development of ethical frameworks, governance models, and cultural maturity that operate on a cosmic scale. We would need to craft interstellar laws, establish protocols for first contact and non-interference, and perhaps most challenging, cultivate a collective wisdom that prioritizes stewardship over conquest. This ethical imperative is arguably as difficult as solving the exotic matter problem. It asks not if we can build the engine, but if we are worthy of turning it on. While these grand questions of cosmic responsibility define the horizon, the practical journey begins with far humbler steps. Our current efforts to reach the stars look nothing like a warp bubble, but they are laying the essential groundwork for whatever may come next. The roar of a chemical rocket is the sound of brute force. For over 60 years, this explosive reaction has been our only way to break free from Earth's gravity. a controlled detonation that throws thousands of tons of metal and fuel against the planet's pull. The principle is simple and violent. Burn propellant to create a hot, high-pressure gas and shoot it out the back as fast as possible. The thrust is immense but fleeting. To reach orbit, these rockets must carry almost their entire weight in fuel, a self-defeating equation that leaves little room for cargo and confines us to the shallow end of our own cosmic pond. It is a technology of immense power and profound inefficiency, like using a cannon to launch a paper airplane. To go farther, we had to think quieter and smarter. This led to the gentle whisper of electric propulsion, like the ion drives that have nudged deep space probes for decades. These engines work on a completely different principle. Instead of a violent chemical explosion, they use solar power to electrically charge atoms, usually of a gas like xenon, and accelerate them to tremendous speeds out of a thruster. The push from a single ion drive is minuscule, often compared to the weight of a single sheet of paper resting on your hand, but it can sustain that feather-light thrust for months or even years, continuously adding speed in the frictionless vacuum of space. Over time, this patience builds to velocities chemical rockets could never achieve without impractical amounts of fuel. Yet, even at their best, these efficient engines are achingly slow on an interstellar scale. An ion-propelled craft might take tens of thousands of years to reach the nearest star. They are the ultimate tortoise in a race across light years. Then there are sails that catch not wind but light itself. Solar sails are vast, ultra-thin mirrors that use the faint but constant pressure of photons from the sun to gain momentum. Like a sailboat tacking against the breeze, a spacecraft can angle its sail to steer, using this free and endless source of propulsion. Breakthrough Starshot, one of the most ambitious concepts, aims to push this idea to its limit by using powerful ground-based lasers to propel a fleet of tiny, gram-weight sails to 20% the speed of light, reaching Alpha Centauri in about 20 years. This represents the bleeding edge of our realistic, near-term aspirations, a blend of brilliant engineering and patience that still accepts the vastness of the gulf we must cross. Now, let us place these remarkable human achievements on a cosmic scale. Imagine the journey of the Voyager 1 probe, the farthest human-made object from Earth, traveling at about 38,000 miles per hour. If interstellar space were a continent, Voyager's pace would be a slow, determined walk. Reaching the speed of light would be like switching from that walk to flying in a jet fighter at over 670 million miles per hour. The Alcubierre drive does not propose to make that walker into a faster runner or even that jet pilot. It suggests we stop walking altogether. Instead, we would pick up the patch of sidewalk under our feet and move it, bringing our destination to us while we stand perfectly still. This is not a difference in degree, it is a difference in kind. Our current technologies, from roaring chemical rockets to silent ion thrusters, are all about moving through space. The warp drive concept is about moving space itself. This stark contrast is not meant to diminish our incredible progress. Every ion-propelled probe, every successful solar sail deployment, is a monumental victory of ingenuity over the harsh constraints of rocket science. These are the essential, incremental steps that expand our presence in the solar system and test the foundational technologies a starfaring civilization will need. They represent the long, hard road of engineering reality. The Alcubierre drive, by comparison, exists in the realm of geometric possibility. It reminds us that while we are mastering the rules of the road, theoretical physics is still sketching maps of roads that do not yet exist. One is the work of our hands, the other is a dream drawn in the language of the universe. To see if that dream could ever be more than lines on a page, we must subject it to the most extreme conditions reality has to offer. The equations are too complex for a pencil and paper, and the experiments too daunting for any lab on Earth. So where do physicists turn to test the geometry of a dream? They turn to the silent, lightning-fast world of supercomputers. This is the frontier of numerical relativity, a field where the universe's most profound laws are translated into billions of lines of code. Here, scientists don't build warp drives, they simulate them. They take the dense, nonlinear mathematics of Einstein's field equations and ask a supercomputer to solve them step by virtual step, modeling how a hypothetical warp bubble might form, hold its shape, and move through a simulated cosmos. Think of it as the most advanced flight simulator ever conceived, but instead of testing aerodynamics, it's testing the aerodynamics of spacetime itself. In this digital laboratory, researchers can tweak parameters that would be impossible to control in reality. They can adjust the distribution of exotic matter, seeing if a smoother, more diffuse ring of negative energy creates a more stable bubble than a sharp, concentrated one. They can test different geometries, from Alcubierre's original design to the oscillating shapes proposed by later theorists, watching in high resolution as these mathematical constructs either stabilize into a coherent wave or violently collapse into a digital singularity. These simulations are crucial for probing the infamous horizon and radiation problems. A supercomputer can model the quantum fields at the bubble's boundary, calculating the energy of the particles that would be generated and tracking where that energy goes. It can map the causal horizon, showing exactly how information becomes trapped, helping theorists understand if there's any conceivable way for a crew to steer or stop the bubble from within. The value of this work is not in delivering a blueprint, but in pruning the tree of possibility. A simulation that consistently shows a particular warp geometry tearing itself apart in a storm of gravitational feedback saves years, perhaps centuries, of theoretical dead ends. It tells researchers this path leads to a cliff, look elsewhere. Conversely, a simulation that shows a configuration remaining stable, even for a few virtual microseconds, becomes a beacon. It suggests that with further refinement, this particular set of assumptions might not be immediately forbidden by the laws of physics. It provides a narrow target for future mathematical exploration. This digital tinkering is where much of the serious theoretical work on warp physics now lives. It is a testament to human ingenuity, using our mastery of computation to explore realms our hands cannot yet touch. While no simulation can ever confirm that something is physically possible, it can powerfully suggest what might be impossible, guiding our aspirations with the cold, clear logic of processed ones and zeros. This meticulous virtual groundwork slowly constructs a map not of a finished journey, but of the treacherous terrain we would need to cross. The distance between a dream and a blueprint is measured in centuries. If the warp drive is ever to be more than a mathematical phantom, its creation will not be a single eureka moment, but a grand, multi-generational symphony of human achievement. We can sketch a purely speculative roadmap, a thought experiment that reveals the staggering sequence of breakthroughs required, each phase building on the last like a ladder reaching for the stars. The first phase is not about bending space, but about mastering the energy to even attempt it. Our civilization must first graduate from planetary to stellar scales of power generation. This begins with the long-sought mastery of nuclear fusion, harnessing the same process that lights the sun to provide clean, abundant energy for a world. But fusion might only be the beginning. The next step could be the controlled production and containment of antimatter, the ultimate energy-dense fuel, where the annihilation of mere grams of matter releases energies rivaling nuclear bombs. This phase is about building the economic and industrial foundation, a society so energy-rich that the astronomical power demands of space-time engineering become a feasible line item in a planetary budget. Only with that foundation poured could we even approach the second and perhaps most profound phase, understanding and manipulating the fabric of reality itself. This is where we confront the exotic matter problem head-on. It would require a revolution in quantum field theory and materials science, perhaps learning to synthesize stable regions of negative energy density in the lab, or discovering an entirely new framework of physics that makes such exotic requirements unnecessary. This phase is not engineering, it is deep science, unraveling the universe's most intimate secrets about what space and energy truly are. Success here would grant us the theoretical and practical tools to become apprentices in metric engineering. Phase 3 would then see the first timid, microscopic experiments. Imagine a future laboratory where scientists don't create a warp bubble, but a warp wrinkle. Using unimaginably powerful and precise fields, they might induce a fleeting, nanoscale distortion in spacetime, holding it stable for a fraction of a second, just long enough to measure its properties with instruments of exquisite sensitivity. These would be the Wright brothers' moments of warp physics, not a flight to Kitty Hawk, but a proof of concept that the geometry can be deliberately shaped at all. Decades, perhaps centuries, of refining these lab-scale demonstrations would follow, slowly scaling up the stability and control of these space-time distortions. Only after all of this, after mastering stellar energy, rewriting material science, and achieving controlled metric engineering at small scales, could the final macro-scale phase begin. This would be the monumental project of integrating all that knowledge into a functional vessel, solving the nightmarish problems of navigation, radiation containment, and controlled deceleration. This speculative roadmap is humbling. It frames the Alcubierre drive not as a machine we might build, but as a potential capstone for an entire civilization's technological and philosophical maturity. It is a mirror held up to our ambitions, asking not just if we can reach the stars, but what kind of people we must become to earn the right to try. The equations are a language, but the dream they describe speaks to something far older. At its core, the Alcubierre drive is not merely a set of tensor calculations. It is a mirror held up to the deepest currents of human ambition. For all its talk of negative energy and causal horizons, its most profound function may be symbolic, reflecting our timeless refusal to be caged. We are a species born under a sky we long to touch, telling stories of flight long before we understood the physics of lift. The warp drive is the latest chapter in that ancient story, a declaration that the universe's rules are not walls but puzzles to be solved. It embodies the audacious belief that a limit written into the fabric of reality is not a full stop but a comma, an invitation to look for the loophole. This relentless curiosity is our defining trait. We are the animals who look at a speed limit sign posted by nature itself and immediately ask, what if we took a different road? The drive crystallizes this spirit into mathematics. It shows that our most powerful tool for exploring the cosmos is not a rocket, but the human mind's ability to wield abstract symbols, to play with concepts like curved spacetime on a chalkboard, and in doing so, conceptualize machines that may lie millennia beyond our grasp. In this way, the drive is a profound gesture of hope. It argues that the impossible is not a fixed category, but a temporary label waiting for a new generation with sharper questions. Its value is not diminished by the fact we cannot build it today. Its power lies in its existence as a target for our aspirations, a distant beacon that organizes and inspires generations of scientists, engineers, and dreamers. It proves that ideas born in the pages of science fiction are not distractions but essential seeds. They give us a destination to aim for long before we have a map to get there. The warp drive teaches us that the line between fantasy and physics is porous, constantly redrawn by those brave enough to take a fictional premise and ask, could the universe allow this? So while we may never ride inside an Alcubierre bubble, the very act of contemplating it expands the horizons of the possible. It pushes the boundary of what we believe can be known or achieved, not by delivering a finished engine, but by nurturing the kind of bold, disciplined imagination that will be required for any future among the stars. Its most immediate gift to our culture is this inspiration, this reminder that our greatest journeys always begin not with a roar, but with a quiet, revolutionary thought. The blueprint for a starship has become a lens through which we examine our own place in the cosmos. We began with a simple, ancient desire to sail the ocean between suns. Miguel Alcubierre gave that desire a mathematical form, translating a science fiction staple into a set of equations that, on paper, do not break Einstein's rules. We then saw the staggering cost of that translation, a demand for a form of matter that warps reality in reverse, and the terrifying revelation that such an engine could double as a weapon of stellar annihilation, sterilizing a destination with a burst of quantum fire. We navigated the paradoxes of steering a vessel cut off from causality and weighed the sobering ethics of wielding such power. Through it all, the Alcubierre drive has remained exactly where it began, a brilliant and provocative theory, a landmark on the map of human curiosity that we cannot yet reach. Its power is not in offering a shortcut to the stars, but in illuminating the vast, uncharted territory we must cross to get there. This theoretical engine has no exotic matter to fuel it, but it runs perfectly on imagination, pushing physicists to refine their models, inspiring engineers to test new ideas, and reminding every one of us that the universe is far stranger and more malleable than our everyday senses suggest. The dream of warp speed, in the end, is less about building a machine and more about building a mindset, one that looks at a fundamental limit and asks a better question. As our probes creep through the solar system and our telescopes peer back to the dawn of time, this audacious concept keeps the ultimate destination vividly alive. It tells us that the journey to the stars will be measured not just in light years, but in the generations of thinkers who dare to sketch the impossible. Where do you see humanity's path among the stars in the next century? Share your vision in the comments and subscribe for more journeys to the edge of understanding.